Good evening to our speaker and to members of both NEMI and the Mineralogical Society of Great Britain and Ireland, and also to those who are attending on the Institute's YouTube channel. Welcome to you all to this evening's lecture. Now, can I first of all call, see if any members for apologies?
Nope.
No members for apologies. Well, in that case, I'll hand you over to our Mr. Andrew Drubansky, our Honourable Secretary, to give us the minutes of the last meeting.
So, thank you very much, Steve. So our last lecture was on the 21st of January, given by our very own Dr. David Bell. Had a excellent, lovely attendance, both on our Zoom and also via YouTube, and it's got a fair number of views since then. Questions were by Bill Bell and David Granger on various aspects of New Zealand. And we have our vote of thanks, Ian Cameron McIntosh, some closing remarks from our president, if the meeting can take that as an accurate record of the minutes. Lovely. On to our notices. Our March Institute lecture is going to be on living construction. This is going to be given by Professor Martin Dade Robinson of Newcastle University. I've seen the work of this research group down at Materials Expo. They're going around trying to make building materials out of various types of bacteria, and it should be a really fascinating talk to see what the house of the future may look like. Don't forget, it's a members-only event. Next Tuesday, we've got our Young Persons Lecture Competition, jointly with IMMM and sponsored by the Armourers and Braziers and the Royce Institute for UK Material Science. We've got several excellent competitors, and we look forward to seeing who will go through to the North East Regional Final. We have a further Younger Members lecture, which will be sent out. That's available for all members, and we'll also be doing it on YouTube. This is going to be by Mark Sanders, who on his work doing biological surveys down south with the British Antarctic Survey. So hopefully you'll be able to join us for an extra additional lecture next Thursday. We also would like to announce our joint conference with the Durham Energy Institute on sort of the Northern Energy transition. This will take place over 2 days on Thursday the 15th and Friday the 16th of April. First day is predominantly organised by our institute. We'll go over a few, climate change in the geological record, but also how geologists can help us explore for the metals that we'll need to supply the material scientists to come up with all these excellent gizmos that they keep on discovering. And also there'll be several sessions and talks given by manufacturers based in the north and those doing research also in the north. So it's how our region is reacting to all of the recent political legislation. And the second day is predominantly going to be more policy based, and that's organised by the Durham Energy Institute itself. So more details are on our website and will be sent around the membership in due course. Don't forget to follow us online. That's Twitter at Mining Institute. All our talks are building up on our YouTube channel, so if you've missed one, don't forget to go and look at that. And my usual notice, don't forget to come along and become a member. Under usual times, we have our monthly lectures in Newcastle. We've got our annual dinner with men and women from a variety of professional backgrounds. Very interesting to talk to. We're developing a range of additional social events, and of course we've got our local regional field trips to the north, and one day we will have our international field trip to go and see some mines in Poland. So don't forget, we've got a range of excellent membership benefits, so if you are interested in becoming a member, do just visit our website mininginstitute.org.uk/membership, fill in the application form, and we'll be in touch. So that's all there is from me, and I'll hand over to Steve to do the introduction for what will no doubt be an absolutely fascinating talk from Hannah.
Well, thank you very much indeed, Andrew. Our speaker this evening has an impressive set of credentials in geology and earth sciences, having an MSc in mining geology from the Camborne School of Mines in 2010 to 2011. A PhD studentship in Cardiff in 2011 to 2015, and was a postdoctoral fellow at the University of Witwatersrand in Johannesburg, South Africa, 2015 to 2016. Hannah's taken up a present post as an economic geologist and geochemist at her alma mater, the Camborne School of Mines, in 2017. Hannah's research aims to understand the sources and budgets of metals and sulfur spatiality and throughout time, to assess how this influences mineralization in the crust. Tonight, Hannah will talk to us about the curious case of bursting Lamprophyres in the mine. So enough of me talking about it. I'm going to hand you across to Hannah now. Hannah, thank you very much indeed.
Thank you very much for the introduction, Steve, and thank you also to everybody at the institution in terms of hosting me for this evening's talk. It's fantastic to be able to be part of that. So I'm just going to share my screen with you at the moment, and please do shout up in a second if you can't see my PowerPoint slides. Thank you to Steve for the introduction, and yes, I'm a geologist at the Camborne School of Mines, but the talk I wanted to give you today was not pure geology. In fact, it's very much an interdisciplinary project that I've been working on for a number of years now. It started off at WITS when I was there, and ultimately I've taken it with me to CSM, and now encompasses a range of people from geologists and applied mineralogists all the way through to various mining engineers, rock mechanics, and there's now even an overlap with biogeochemistry, which is unbelievable. So yes, the curious case of the bursting Lamprophyres in the mine. I should premise this by saying that this is based in a platinum mine in South Africa, in the Bushveld complex, but for NDA reasons, I'm not going to tell you the mine, unfortunately, though maybe some of you can guess where it is. Of course, this is a teamwork, as I've already alluded to, and there's actually quite a long list of people who are involved in this now, so it's fantastic to work with them all. Really, it's a collaboration between CSM and the University of the Witwatersrand, and a couple of companies in the Bushveld as well who are actively mining in certain portions of it and having problems with outbursts. So there's lots of people beyond those who are listed on this slide who we really collectively all work together, and I'm here representing all of them to tell you about this today. I should also mention that much of this work, including at the moment, is sponsored by the Royal Academy of Engineering, and in the past we've also received quite a lot of funding from the NRF in South Africa, amongst others as well. So I'll start off the tale by something completely unrelated, and that is when I was a postdoc at WITS. My research interests entirely lay in understanding how metals move around in the Earth's mantle and how that basically predetermines possibly how mineralization occurs and where it occurs. So it's this idea of metallogenesis, and there's lots of kind of chemic stuff in terms of mantle xenolith. Often they're very mica rich, and in many ways they're related to kimberlites. When I was at WITS, basically the Lamprophyre kind of area of research for South Africa was a bit of a blank canvas. There's lots known about the kimberlites, but when it came to these slightly weird rocks of Lamprophyres, nobody really knew very much. And so that's where I started my research. And I put out basically a request to a whole bunch of mines around the Bushveld, which is also one of my interests, and said, has anybody ever heard of Lamprophyres, and do you have any? And if you do, please can I have some and take some samples and work on them? And within half an hour, I got a flurry of responses from a whole bunch of mines who basically said, and I remember one quote in particular, Lamprophyres, everybody knows about the Lamprophyres, even the typists in the office know about Lamprophyres, they're such a pain in the ass. So yes, of course you can come and sample them, but on one condition, and that's that you have a look at some of the more engineering and safety related issues that seem to be linked to them, to the Lamprophyres. So I said, yes, that's fine. I'll scratch your back if you scratch mine, that's fine. And so really it started from there. So I've got a couple of pictures of what the Lamprophyres in inverted commas look like in core. And some of you, if you're geoscientists, may also see that there's quite a strong resemblance to orangiites, which is a type of kimberlite as well. So they're all kind of interconnected in terms of their lithology. And they kind of had this glittery appearance that comes from there being so much mica within them. But also you see these kind of black or grayish green spots in there. Those are a mineral called olivine, which have normally become altered and broken down. And you may also see that there's kind of a stripe or veining effect through them, and there's some carbonates and carbonate minerals in there as well. So that's what they look like. And as you can see, sometimes they're quite competent, they're quite nice and hard rocks, but more often than not, as you can see on the top right, they're incredibly friable. And that represents one of the hazards underground associated with them. And certainly anybody that's worked on a kind of diamond project may be familiar with falls of ground associated with kimberlites, probably related to the fact that the micas are essentially rotting out of the wall, in terms of the micas are becoming oxidized and turning basically to clays, and so they fall apart like that. But actually the main danger, other than falls of ground underground, is associated with these outbursts. And at the time when I contacted the mines, they seemed to think that there was a relationship between where we see this lithology, this rock type, the Lamprophyres, and where they have seen outbursts, I'm using the word quite generally there, underground. By this, I don't mean rock bursts, so not Witz Basin style rock bursts, and I don't mean explosions in that there's no ignition that they could see was taking place, but rather outbursts as in some kind of pressurized gas or something rapidly releasing, and in the process it was blasting out a whole bunch of rocks down various developments underground in an uncontrolled way, and it was kind of dangerous in terms of people operating underground, of course, but we'll get onto that story in a bit. For a little bit of context, I thought I'd put in just a kind of generic diagram of how Lamprophyres and kimberlites look underground in terms of their map and their mapping and plan view orientation. In plan view, you can see that we normally have a series of dikes, so long conduit-like or fissure-like bodies, and they're very difficult to predict or follow underground because they tend to jog or jump and bifurcate and anastomose, whatever term you want to throw at them. They're not easy things to follow, and so we can't really predict very easily where they are. All we can do is, okay, we encounter one, maybe it's a few centimeters wide, we'll encounter another one a little bit further away that's maybe a few meters wide. They're quite variable, and they're, as I say, quite difficult to follow underground. And in plan view, this is what we're looking at. And this is an important factor because if there is a relationship with these dikes, actually being able to follow them underground in the first place is nigh on impossible. So we have to look to some other method to do this. I thought I'd also show you a couple of pictures of the dikes underground in terms of their general appearance. So on the left-hand side here, you can see that the dikes obviously been marked up with this with the yellow paint, and so we've got the dike running almost vertically on one of the side walls here. They tend to always be vertical or very steeply dipping, and typically they're in the region of 0.5 meter to 2 meters in width, but they can be down to a few centimeters that you can still recognize them in. Often you see that they are kinked or bent in some way, and in some cases you can see that they've kind of ripped up xenoliths and bits of wall rock from the surrounding bushveld. So these dikes are younger than the bushveld that they're intruding into. They're nothing to do with the mineralization in the platinum mines, and we know from dating them that they are substantially younger than the bushveld. The bushveld is 2 billion years old approximately, and these dikes are about 140, 130 million years old. So there's a massive age difference there. They are two entirely separate geological events. Okay, so that's a little bit of background in terms of what the Lamprophyres look like and what these dikes look like. And as I say, I've got into this from a slightly odd trajectory in terms of why I ended up looking at outbursts. But nonetheless, having gone to the mine and asked, can I sample, they then presented me with something that similar to what you see on the screen at the moment. And this is essentially the kind of number of outbursts that they were dealing with and why they thought that the outbursts were associated with the Lamprophyres. So at the time, well, actually not quite at the time, we've added up a couple extra there, but broadly speaking, there were about 100 outburst events that had happened by that stage. It's now up to about 120 something at this particular mine. And if you kind of plot them according to what geology is around in that area, then we can see that there's a couple that maybe happened with potholes associated with the platinum reefs. maybe these things called erupts, which is iron replacement ultramafic pegmatite, which is a really long name and actually irrelevant to the talk, but some other lithology that's bushveld related. We've got a couple that are related to dolerite dikes in the area, but the vast majority of outbursts seem to be associated either with joints, shears and faults, and they lumped all of those together, or with these Lamprophyre dikes. And often the Lamprophyre dikes, I should mention, actually are intruded along and follow faults. So there's a linkage there as well. We also went to go and have a look at, started to uncover bits and bobs of information that they've been recording, and had a look at the number of triggers for methane being detected underground. So this is as either a fixed sensor or as a personal sensor. And these are just flammable gas sensors. So they're pretty much only detecting methane. And again, the number of events that were outburst events that were being recorded, in the vast majority of cases, there was no signal that this was going to happen. In terms of, there was no methane, there was no gas alarm going off underground saying danger, whatever. There was no indicator, it just happened out of the blue. So this was interesting because it kind of told us either that the volume of gases was too low or below detection limit for those fixed sensors, or that the gas isn't methane. That's the other point, is we didn't know what the gas was at the time. We don't know what the species of the gas was. We also could be presented with a bunch of facts in terms of the number of events that were happening across this whole mining area, according to each of the shafts. And I've removed the shaft names, but each of these bars is representing a different shaft. As you can see, some shafts were particularly problematic, others, there was basically no problem there at all. And so there's a kind of geographic element to this in terms of this, or a spatial element to this in terms of certain shafts seeing more of these outburst events than others. You can also look at depth underground. The number of outbursts seems to be more substantial in terms of the deeper you get, the more risk you were, or the more likely you were of seeing an outburst. And so somewhere in the region of about 900 meters, 800 meters and below is where you really start to rack up most of the numbers for these outburst events. So again, we're getting a little bit of a spatial handle here, and we see that there's a link to these Lamprophyre dikes. We see there's this kind of lithological link. You can also boil down the stats in a whole number of extra ways, right? And whether this is meaningful or not, you can do it, number of events per year. Okay, we can see that really the problem started at the mine around about 2007 with a massive outburst. I'll show you some pictures of that. And then in 2008, these things were becoming more regularly noted. Now, that could be a bias of the reporting system. It could also be a human bias that once something is seen as being a problem, then it's going to start entering into reports. Okay, something went wrong for some other reason. Maybe it's an outburst. We'll put it down as an outburst on the report. Or perhaps there's something we can't explain and we'll put it down as an outburst anyway. These are some of the issues with the records that we have, but nonetheless, we can see that the number of events seems to change over the years, and really 2007, 2008 was the first time that these things were really being picked up. You can play the trick of doing it according to number of events per month and days of the week, and there are good reasons for trying this. There may actually be some kind of atmospheric control on outbursts, a little bit like a barometric pressure drop that one might look into in terms of in a coal mine. Days of the week, maybe there's something around the actual operation of the mine and the scheduling that means that we see certain outbursts being more likely depending on what you're actually doing underground at the time. And that probably is true for some of the bigger outbursts. So this was where we're at, really. We were presented with a bunch of facts. We've got some Lamprophyres, and basically it was a case of, right, well, what can you do with all of this? Because this is becoming quite a problem, and being quite a problem in terms of health and safety underground, of course, as well. So our aims and objectives throughout this study, and this continues to be the case, were really to identify the composition of the gases that were associated with outbursts. We didn't know that. The mine didn't know that, and there was this link with the methane sensors that didn't really seem to help very much. Identify the causes and mechanisms of outbursts. Is there some specific geological structure or combination of structures and lithologies that are, really the control for an outburst? You need all of those ingredients to come together in order for an outburst to occur. Is there some kind of zone, perhaps, we can identify as being a particularly high risk and prone to these sorts of outbursts, or quite a gassy area. Also, can we develop a method to forecast the outbursts and thereby basically kind of help this sort of safety situation underground? And by forecasting, we need something to kind of pin that on, but better than just, okay, this area is high risk. We need, maybe there's some kind of indicator we can use. And also then identify precautionary measures in order to mitigate risk and injury. And I'll go into those a little bit later on. But first, I thought I'd show you the aftermath of some of these outbursts. The pictures that you see on the screen at the moment are the result of quite a large outburst where several 100-ton of rock was blown out as basically a secondary event from a controlled blast. And this was about 2 years ago now, where when this happened. And effectively, in the outburst, what's happened is the rock has pulverized itself. There was kind of like this mica-y sand for miles down the drive, but it's pulverized itself, and the void that you see left behind is essentially where the dike used to be, where this Lamprophyre dike used to be. And actually, the wall rock on either side, there's the thinnest skim of Lamprophyre, but otherwise it's just bushveld either side. And you can see sometimes this there's sort of flakes of it. Often these dikes are kind of banded or composite dikes, and sometimes you get that sort of leftover edge bit or margin of the dike still stuck after some of these outbursts. And this is quite a big hole. If I can transition onto the next slide, this is a stitched photo that goes along and then up into the back. And they reckon it was around about 11 meters in length. They couldn't reach the top, and there was a fair old drop, and I didn't really want to find out how deep that was. And we know it was several meters. We couldn't go any further. And there was this bank of kind of this mica-like sand. In other cases where we've had large outbursts, of course, it causes all manner of damage and destruction underground in terms of the any of the utilities down there. So this is reinforced ducting that's just been chucked several tens of meters along and twisted in the process. There are whole blocks of rock. In fact, there's one that the company has at surface. They brought it to surface and put it outside their offices, which was part of a big event in 2007, actually the first one that really sort of got them to sit up and think about it. And in that case, you know, that's several tons of rock just in one block that's been chucked, at least 50 meters in that case, straight down the drive. Now, because these events these big events are happening as a secondary factor or a secondary event after a controlled blast, then thankfully, when it comes to these big events, there have been no injuries or fatalities. Everybody's already out of that, ready for the blast, and then they come down and find there's a bigger hole than they expected. But there are some other worse, in terms of from a human point of view, some other worse systematic or symptoms rather that go on because of these outbursts. So I'm just gonna, I don't know if this is gonna play, but I have included this slide, not for necessarily you guys, because I've given this talk a couple of times. And for some people who have never been underground or aren't particularly familiar with the sort of mining industry at all, then this idea of an air leg is a little bit alien to them. So I thought I'd find a video from, this is from the other CSM, this is from Colorado School of Mines, but nonetheless, it's still relevant. I think my internet's not going to let this work. Yeah, it's not going to let it work. I'm going to have to skip. Sorry, my Cornish internet is playing up a little bit, so it's not going to be able to do that. But anyway, you get the point. You've got an air leg, and what was happening was there was a series of smaller outburst events that were associated with where the driller was going in, hitting what can only be assumed to be a pressurized pocket of gas, and the drill bit was being forced out. The whole drill was being forced back out onto the driller behind, and in some cases that was smacking them right in the chest. In some cases there were shrapnel wounds, pepper wounds coming straight down the drill bit and into their face if they're not wearing their face mask or their glasses. Then there was a few cases of blinding. In other cases, and very sadly, there have been individuals who've been thrown back so hard that they've actually then hit behind them, and that has led to a fatality, very sadly, in one case. So counterintuitively, it's the smaller pops, if you will, these small little outburst events that are particularly dangerous to individuals. The very large events much as they're scary and dramatic, so far they don't or haven't presented a risk to, or actually haven't resulted in any injury underground. Although the big question is, what if, I suppose, what if one of those were to go off when you were underground in the vicinity? So just pausing a second then, we through the records and through looking through this stuff at the mines, we can basically categorize these outburst events, all of which seem to be associated with shears, faults, and Lamprophyres, with one or two exceptions, into very large events and small events. And you can see how they're divided on the screen there in terms of the large events as secondary to a controlled blast. There's no injury or fatality, but they're expensive to deal with. Whereas the smaller events are the ones that are really nasty on an individual basis. So this is what we're working with. We have these sort of two scales to deal with. So that's the problem in terms of what's going on underground. Now, what are the gases? Well, gases can be included within rocks or hosted underground in a couple of different forms. For example, they can be included as tiny little bubbles or fluid inclusions, often within minerals like halite or carbonates, calcite, for example. And effectively, these are just little bubbles of volatiles or gas, sometimes liquids, that have become trapped in the rock as it's crystallized. And in some cases, they can be overpressurized. And actually, outbursts in salt mines mean that a series of overpressurized fluid inclusions, once somebody starts digging into them, that pressure is released and it triggers a chain reaction. And you often end up with wormhole-like void spaces after an outburst. So this is one line of inquiry. The other way that we can generate rocks underground is by some kind of chemical reaction between the minerals that are making up that rock. So, for example, I mentioned that there was olivine within these Lamprophyre dikes, and the olivine had largely altered. When it alters to serpentine, there is a production of gas associated with that. So that's maybe one way that we can generate gas. There's also a whole bunch of other mineral reactions that can generate things like methane, carbon dioxide, hydrogen, amongst others. The third way that we might find or generate gas of various different types. So the biogenic gas, basically, as the mine guys put it, it's bugs, right, who are controlling this reaction, and effectively they're outputting gas as a byproduct of that. I think one of the mining geo guys just said bug fires, which probably like sums it up reasonably well. Okay, so we have our methods of generating gases underground and perhaps hosting them as well. In terms of physical state, then I say gas a lot. It could literally be a physical state of a gas. More generally, it could be volatiles that are a combination of gas and liquids. It could be gas and condensate. There's a couple of ways that we can look at this. When we have an outburst event that either reflects that we have an overpressurized system, then we're releasing the pressure on that triggering reaction, and so it's releasing the pressure. Or it could be that we're also changing the physical state of the elements or the volatiles that are hosted in that environment, and that change in physical state then is associated with a change in volume. So we're going from liquid to gas. That will mean that we increase the volume, and so that could also be the trigger. I've mentioned salt mines just as an analogy there, and here's a couple of pictures of some cases where we see voids left after outbursts in salt mines, and this is triggered by fluid inclusions, overpressurized fluid inclusions. And individually, they're tiny. They're perhaps a millimeter less than a millimeter more often. But cumulatively, once we've got this chain reaction going, they're quite effective means by which to end up with this kind of void. And so this is really where we started with our investigation in terms of why the Lamprophyres seem to be associated with outbursts, because we noticed that there was quite a lot of halite and anhydrite, so sulfate minerals, and sometimes carbonates that are within the matrix of our Lamprophyre. So if you look at this under a microscope and you do the mineralogy, then you have a series of what I'm going to loosely call primary minerals. These are minerals that are part of the kimberlite or Lamprophyre, rangiite, however you want to term it. They're things that ultimately crystallize from a magma. And then around those crystals, what we often find is that there's replacement by secondary minerals. And those secondary low temperature minerals like halite and carbonate and anhydrite are very good at having fluid inclusions trapped in them because of the nature and the way that they've been crystallizing. And so actually, having observed that there's brines also coming out of some of the fault structures and that there's quite a lot of salt around associated with these dikes, we thought, right, let's go and have a look at the fluid inclusions. Maybe there's something in this in terms of an analogy to a salt mine, because the methane thing hadn't really shown up anything. So we were a little bit lost in terms of an analogy to a coal mine, for example, or even the gold mines in the Wits Basin. So I should highlight here that a lot of what I'm going to show you next is actually the work of an MSc student at Wits. She's now completed, her name is Priel Dyer, and she's now actually doing her PhD over in Nova Scotia. So this is a little bit of a change of scene for her. But she did all the mineralogy on these dikes, including looking at some of these secondary minerals like halite, like calcite, like anhydrite, and ultimately characterize them all. So we've got a couple of thin section pictures on the right-hand side here. And this hopefully also demonstrates the variability of the Lamprophyres as well, in terms of they're quite, although they all kind of look glittery and, you know, sort of a browny black color in hand sample or in underground or in core, actually when you thin section them, you see there's a fair old range of the mineralogy. So sometimes they have these green clinopyroxene crystals, and then these micas, and then everything else that's white in this picture, if you can see my mouse, is basically a combination of halite and anhydrite. Then on the right hand side here, we've actually got little pockets of calcium carbonate, sorry, so calcite, again, hosting fluid inclusions. Sometimes we see it as veins, and also there may be some fluid inclusions associated with the serpentinization of the olivine. So this just gives you a little bit of an insight into the look of the dikes. But I mentioned that sometimes there are sort of patches of secondary minerals, and sometimes these can be quite big. And actually, going back to that 2007 big outburst event, another bit of rock that got chucked out of that was a sort of football-sized geode of halite and anhydrite and natrolite, which is a zeolite mineral. It's a low temperature mineral again. And in this example, we can actually see we've got largely natrolite and halite intergrown in here. And we've actually got in these grey areas, little bits of the Lamprophyre itself associated with that. And this sort of football-sized geode got us thinking, okay, well, maybe there's some void space. Maybe there's obviously space for this thing to grow and the crystals to grow nice and euhedral, like we see them there. And also, there's going to be loads of fluid inclusions in this. So let's go and see what that can show up. And so Priel did her fluid inclusion work. This is where you have a little slither of rock, hopefully thin enough that you can pass light through it, and put it on a very high power microscope in order to zoom in on the fluid inclusions, which are often, you know, definitely sub a millimeter, more like a couple of microns or tens of microns across. And if you zoom in on them, what you find is that you have, say, a couple of different fluids that are entrapped in there. Sometimes you have some solids as well. So she's got a vapor bubble labeled V in here. So this is basically, it's literally a gas bubble. She's got some liquids around that in the rest of the fluid inclusion. And then she's actually got a little solid crystal in here. So this is probably a salt crystal of some description. And all of these are cohabiting in these little bubbles that are trapped within the rock. And effectively, she can undertake microthermometry. This is where she would heat and then freeze the stage of the microscope. And by watching how these things homogenize, so basically where this vapor bubble disappears entirely, you can calculate what the composition of the fluid inclusion is within that little bubble. And, you know, it kind of worked. We got some numbers for that, and we sort of vaguely thought, well, there's probably brines, there could be some carbon dioxide, some methane, but these are really difficult fluid inclusions to work with. Fluid inclusions are always difficult to work with. These were particularly tricky. And even if we threw something like Raman spectroscopy at it, it was very difficult to get a composition of the fluid inclusions on a one-to-one basis. So this meant we had to resort to, or rather Priel had to resort to, gas chromatography. So this is a bulk method now. Rather than looking at these rocks under a microscope and looking at very specific parts of them, we're now just going to take a bit of rock, crush it up, and measure what comes off of it as a whole. So we used what's called inline gas chromatography, and this was actually carried out in Nova Scotia, where Priel is now based, in a lab there with Jake Handy. And effectively what we do is we take a little bit of the rock, we clean it very thoroughly, and we put it into a little cylinder. And the cylinder then is hooked up to our gas chromatograph, and effectively you just crush the rock. And by crushing it, mechanically crushing it, you're opening up things like the fluid inclusions that are within that, and immediately sucking away any gases that come out of those fluid inclusions straight into your instrument, the gas chromatograph, so you can analyze the gases that way. So everything's basically contained within the system. We can't have any atmosphere getting into there. So Priel did this on lots of samples, and I should add the caveat that depending on the setup of your gas chromatograph, it depends on what gases you can actually look for. So you can't analyze all gases at the same time. You have to analyze for certain gases for one run, and then using a slightly different method or different instrument at the end of it, you have to analyze for a suite of other gases on another run. And one of those methods meant that we couldn't distinguish between carbon monoxide and carbon dioxide, but we could tell if there was carbon plus oxygen-based gases, water, methane, and we could probably tell a couple of other bits and bobs as well in terms of other hydrocarbon-based gases too. So she looked at basically samples of dikes that had come from where there are outbursts, and then samples of dikes where we knew had never been an outburst anywhere near them. And she could see that there were some differences, perhaps it depends how much you want to read into this in terms of the amount of methane that she actually found. But basically we could see that there was a bunch of gases that were largely methane based that she could measure, and then there was also carbon monoxide / carbon dioxide. We couldn't really distinguish between those two. But she could also see on a sample by sample basis that there was quite a bit of variability on a sample by sample basis, but it just wasn't systematic between whether it was outburst or non-outburst samples that she was looking at. So this was interesting from an academic point of view, and certainly very interesting from the Lamprophyre point of view. But given the difficulty of analysing the fluid inclusions, that there weren't that many, that the gases that were coming off them didn't seem to be that different between outburst and non-outburst localities, we thought we might try another approach as well. So I'm going to leave the in situ gas chromatography world and bulk gas chromatography world for just a second and show you a couple of gas chromatograph records from underground. So these are fixed sensors underground in one of the shafts. And what we can see here is we thought, well, maybe we can see in the gas chromatograph that's fixed underground that we'll see some kind of spike in the gases that are associated with outbursts. And so we plotted this up over time. So we just have a time basically running along the x-axis here versus, in this case, methane along the y-axis. The fixed chromatographs are basically only sensors for methane. That's all they analyze for. And we sort of plotted this through, and I've indicated here between the red and green line where an outburst event happened. And there's nothing particularly obvious to say that in that fixed GC record, there was going to be an outburst. We can see where there's regular blasts, controlled blasts. We see a big spike in the GC record just after that. Fine, but there's nothing spooky going on. There's a little bump here, but it's not particularly meaningful. And actually, if we go and have a look at equivalent GC records for other shafts, for other outburst events, then we see the same. We don't see anything in the GC. So this was showing up a bit of a dead end. Here, for example, I've got the another outburst event that's highlighted here. And I'm showing the GC records for two shafts that are either side of where this really happened. And again, there's nothing to indicate anything amiss in either of those. There's a couple of interesting changes in the overall record that I suspect is to do with the sensor itself rather than what's going on at the mine. So we thought we'd take a little bit of a different approach here, and we'd use a personal device, a Draeger XM 5600 for what it's worth, which is a multi-gas detector. It's a personal device that Draeger have off the shelf. It has 6 ports, so it's able to simultaneously detect 6 gas species, and you have some flexibility with what you ultimately set it up to try and detect. But importantly for us, you can put it in a cradle and you can hook it up to a hose, and that means you can put that hose somewhere. So we thought, right, we'll see if the company would mind drilling us some holes, and they very kindly said yes. And they drilled us 4 boreholes that were horizontal, a length of about 3 meters, and they went straight down the middle along strike on these Lamprophyre dikes in the vicinity of some known outburst events that had previously happened. And then they capped off the hole. And so if I show you that, oh, I seem to have skipped, bear with me. So we had these holes that were drilled for 3 meters. They capped them off with a valve and left them for a bit. And then we could turn up with our swanky Draeger sensor hooked up to a hose. And effectively all we did was shove the hose as far down the hole as we could get. The reason this was 3 meters is because the dikes are incredibly difficult to follow. And that's the maximum distance we worked out. We could actually follow these things into a face and then not lose them. So all of the holes went straight down the middle of these Lamprophyres because of the reasons I've previously mentioned. We could undo the valve at a given date, shove the hose down the hole and start measuring 1 analysis per second for 6 different gases. I should mention the gases that we measured for were methane, hydrogen, carbon monoxide, carbon dioxide, nitrogen and chlorine. Oh, and hydrogen sulfide, sorry, as well. There's a 7th gas there we can swap on. And so we did this about 3 times on all 4 of the holes, and sometimes we closed them up for a week, sometimes we closed them up for a day. On one occasion they got closed up for 2 months, and that was probably a bad idea in hindsight, but nonetheless we thought they'd left them open. So if we have a look at the results then, and this was a really interesting moment because it kind of told us something totally different in terms of these gases are actively moving around underground. These are not fixed pockets. They're not fluid inclusions that are entombed until somebody goes and digs them out. These things are moving around underground. And the way we could tell that was on these sorts of time resolved plots for the gas concentration as we shoved our sensor down those boreholes. So on the y-axis here, we've got concentration of the gas, and this is a plot for hydrogen. On the x-axis, we've got the time, and we've basically taken a measurement every second. So we've got a measurement along, I hope you can see my mouse, but on the sort of 1020 to 1022 sort of time scale here, we've got a measurement of just the ambient gas composition underground, away from the hole. And then we've opened up the valve, we've opened up the tap, and we've shoved the hose down the hole, start measuring. You see this big spike in hydrogen. And then we left the hose down there for about anywhere from 15 to 30 minutes just to see what would happen. So the reason we get this big spike is because these things, the holes have been closed off. So gas has been coming into the hole, it's been filling up that void space. And as soon as we shove our probe down, we're measuring this kind of accumulation of gases in that borehole. But what was really interesting was if we left it in there for a fairly long period of time, certainly long enough that these holes would have sort of aired out, we still see that hydrogen is being emitted from this dike. And because we've got basically a borehole that is entirely lined by Lamprophyre, that gives us a really nice big surface area by which we can get the gases to come into that hole and actually measure them, stand the best chance of seeing these things above detection limit. So we know we've got hydrogen. We also know we've got methane. This time on the y-axis, we've expressed it as low explosive level. So 100% is basically 5 volume percent in terms of concentration of methane. And again, partly because it's difficult to tell on the scale here, but we were actually seeing elevated levels of methane for as long as we wanted to leave that sensor down the hole. So it is streaming out underground. We can do the same trick for carbon monoxide. Again, we see a peak, and then we can see that it sits elevated. Because of the scale, it's a little bit difficult to see that, but it is sitting elevated above what we would normally expect. And we can bring all these things together. So here's a couple of individual dikes, each with a hole drilled down it. And each of these plots is showing on the top here carbon monoxide and methane. And there's also hydrogen plotted in a blue line. And on the bottom plots, we've got chlorine and carbon dioxide. Carbon dioxide, it seems, is not being emitted by the dike, but it also turns out that's quite a handy way of telling whether we're analysing properly as down the hole in terms of the gases that are being emitted, as opposed to just generally ambient in the tunnel or wherever it is that we're underground. So yeah, I suppose the take-home message from these plots is methane, carbon monoxide, and hydrogen are actively being emitted through the dikes, not necessarily from the dikes, but through the dikes. And so this kind of made us rethink this whole fluid inclusion thing. The fluid inclusions weren't really showing much from Priel's work in terms of being reasonable triggers for these outbursts. And certainly this would marry up with what we see in the real-time analysis, because we can see that gases are flowing out. If it were fluid inclusions, we wouldn't see that leakage. unless there was actually an outburst. And as I say, we did this for a couple of different holes. We did this over a couple of different years for different periods of times that we closed up the holes for. And in a nutshell, I don't want to get into too much detail on this, but in a nutshell, what we see is that the composition of gases, so like the ratio of methane to carbon monoxide to hydrogen, does change between the 4 localities that we could measure. And it also seemed to, in some cases, change a bit over time. So it wasn't always the same ratios of gases we were measuring. There was a little bit of variability there. And actually, that's something that we would like to look into a little bit more in the future. So I've probably said most of this already, and I'm not going to dwell on it for too long, but the take-home messages at this stage are basically the 3 main gases there: hydrogen, methane, carbon monoxide. So we know what they are now, at least. The question is, where do they come from? Is it biogenic, or is it abiogenic in terms of, is it coming from some kind of thermal reaction or whatever? But it kind of represented a step change in terms of, these are effectively gas conduits that we're dealing with, according to them being permeable and porous. And so we can move away from this kind of physical void idea. It's not to say that they're not there, but certainly the control seems to be around this movement of gases and blocking that system up. And actually, this marries quite nicely with the geological evidence in terms of the main features that were occurring or being seen around outburst events, being basically pathways for gases. So low porosity, low permeability, high porosity, high permeability pathways. So faults, dikes like the Lamprophyres that are porous and permeable, joints and shears as well. So the next question then is, well, having done all that, what can we actually do about it? How can we forecast it? So one of those questions was, are these outburst events clustered in time? Is there like a way that we can say that a certain period of time, or if you see a certain set of indicators, perhaps you've already had one outburst, would you expect to see another outburst? And we can kind of plot the number of events on these sort of cumulative event plots that you see. So on the y-axis now, we've got the cumulative number of events, and then we've got time along the y-axis from 2007 through to 2019. And this is a trick that volcanologists use to try and forecast eruptions, but effectively you can see that we've got some steps here. And the plateaus show that we have no outbursts for fairly long periods of time, and then all of a sudden we get this sort of stepping up. We've got lots of events, and then we plateau again, and there's nothing, everything goes quiet. Which is kind of indicated by the red lines there in terms of areas where we have lots of events clustering. And we thought we might try and put this in time lapse. So at the risk of breaking the internet, I'm just going to see if I can get a video up. I won't play it all. But each dot that you see appearing on the screen at the moment is an outburst event happening. And if you look on the lower left-hand side, you can see the number of events counting up. You can also see the dates. So we're in 2011 now. And this is a rotating view. So each of the red lines is a shaft. We're moving around. We're looking, roughly speaking, south-ish now. And we've got a vertical exaggeration, I should say, of times 12 here, just so we can see what's going on. And the number of, we're not going to be able to replay this lots of times, although if you're interested, I can certainly send you a copy. But what you'll find is that there's lots of events that happen. This whole thing lights up, and then everything goes quiet, like now. There's nothing happening. It's probably because we've maxed out the number. But then there'll be lots of events again. And the reason that you see them all falling along one plane is basically representing that these things are mostly occurring where we see most mining activity, right? So this is mostly on reefs, Morensky and UG2. I'll close that one a second. So yes, there does seem to be a cluster of events. What that means, I think the jury is still out, but we're starting to get now towards this idea of understanding that the controls on outbursts, and maybe we can use that towards a forecast. So on the note of a forecast, what are the real-time parameters or indicators for something going amiss and there being a higher risk of outbursts? And ultimately, the mind would like us to create a risk map. So I think this is fair to say that it's a work in progress. But if we work through and recap some of the sort of fairly basic things that we talked about in terms of the risk ranking, we could just do this on some fairly basic indicators like, you know, is there some faulting? Is there a Lamprophyre dike? Are you below a certain depth? You could start factoring in certain things around certain shafts or geographic areas of the mine. If you do that, you're probably going to end up with huge swathes of the mine being marked as higher risk, which isn't particularly helpful for anybody. So I think we probably need to look to something a little bit more detailed, a little bit more refined here. And there's a couple of areas that we're looking into now, and this is really bringing us up to date with where the project's at the moment. One of those is a forecasting tool, basically testing whether a kind of coal mine barometric pressure approach can be used in the platinum mines here. Whether it's the same mechanism for outbursts, I'm not so sure, but it's certainly something to have a look into. We have good weather records from just up the road. We have pressure sensors or barometers at surface and down underground. Is there some way that we can look back through the records of the barometric pressure, plot those up according to when there's outbursts? If we see a certain change over a set period of time, perhaps that's one way that we can look into forecasting. But another exciting area, I think, of where we're looking into forecasting now is actually modelling around some of the rock mechanics. And so this is really John Coggan, a professor at Campbell School of Mines. This is really where he is crucial to this. And together with an MSc student last summer, Alda Chimuku, looked at modelling some of the tunnels underground and trying to model what the stress changes were around the mining methods that were being used at that site. And if we know the dikes are oriented in a certain direction, if we know that they're effectively carrying gas continuously, is there something we can do to look to change what's going on underground in terms of the operations, in order to, even if an outburst would otherwise be a possibility, that by changing that working method that we're going to avoid the sort of catastrophic outbursts, or perhaps even the smaller pops as well. So this is very much a work in progress, and I flag it only because I think it's going to be really exciting over the next year or two to see where this goes, because I think this is the real nub of it in terms of the actual practical implications for what can be done about this problem. And so the last slide then is basically just highlighting where all of this is going and our future work. So we've come a long way from basically establishing that the Lamprophyre dikes are not the be-all and end-all to these outbursts, but they are certainly a significant factor because they act as gas conduits. And the gases are streaming out underground constantly. They're not kind of entombed in fluid inclusions or voids. But we don't know where the gases are coming from. We know the species of gases, methane, hydrogen, carbon monoxide, but are they produced by bacteria? Are they biogenic? Are they produced by some kind of thermal reaction? Kind of how old are the gases? All of these things may have actually some quite interesting, obviously academic implications, and some of you may be familiar with the work that was done in some of the Wits gold mines in terms of the provenance of the biogenic gases in that case. But they may also have some very practical implications as well. Also the rock engineering, as I've just briefly outlined there, and actually coupling that with some seismology work led particularly by Musa Manzi, who you can see in the centre here, who's a professor at Wits. And marrying that up with some of the geotechnical work as well. Pat Foster, somebody mentioned him earlier. Pat Foster is involved in this very much in terms of safety and from the mine planning side. And of course, I mentioned the forecasting as well, the possibility of using something like barometric pressure change in order to contribute to this kind of risk mapping / forecasting. And ultimately, this thing has grown. So we now will soon be appointing a PhD student at Wits, who will also be coming to CSM for a little bit, working with the team over in Canada. We've also branched out into links in Toronto and Princeton, and we've got a series of MSc projects at Campbell School of Mines as well. So it's an absolute pleasure to be able to present all of this, which actually represents a lot of work over a lot of years from a whole bunch of people, and it's still very much a live story. So it's been a pleasure presenting to you guys today. I hope it's been of interest, and I will leave some conclusions up on the slides just for now. Thanks.
Excellent. Well, thank you very much, Hannah. I'm sure everyone very much enjoyed that. This is a fantastic overview of all sorts of interesting research. And of course, barometric pressure was something noticed in the northeastern coal mines by our own institute in I think the early 1850s, I believe. That was something that was quite important. I suppose, Steve, move on to questions. So does anyone have any questions for Hannah?
Hi, John Theobald here. Hannah, we could have done with you at Bolby Mine 40 years ago, when I first started out in my mining career. We had large gas outbursts with these classic sort of inverted cone type structures coming through. We didn't have the advantage of some of the equipment you had, the Draeger, for example, but we had gas sampling pumps where if we hit one of these things, somebody would be dispatched, quite often me, with a rubber hose and a tube, and we would pump the gas into the tube and analyze it. And we came up with, methane and some of the heavier hydrocarbon gases, propane, even some pentane, I think. But a lot of the gas was nitrogen that was in there, and that wasn't just a function of bad sampling. I think that was built up for quite a big database. I think one of my questions would be, while there were clear pathways, and I know that in the salt and the evaporites, it's quite difficult to identify structures, but nevertheless structures were there, which provided pathways into areas which would trap the gas. And quite often in the potash mine, it was in shale-rich areas, where the view at the time was that the gas was adsorbed somehow onto the surface of that shale. It's been a long time since I've been there, but I just wondered if you've got any thoughts on the sort of adsorption sort of aspect of these gas outbursts.
Yeah, the absorption thing is also something I think that overlaps in coal mines as well, if I'm correct. And I have to say I'm not particularly au fait with the coal mines scenario, because we quite quickly moved away from that in terms of a mechanism. But it is something that I think we should probably look into. So I'm not sure I can necessarily help or comment in terms of your particular case for absorption there. Sorry.
It's okay.
Do you think this might be a problem in the potential sort of serious Anglo-American mine that's being built, or is it?
Well, I think. Sorry, can I jump in there? The polyhalite contains very little in the way of shaly material, which was always the issue when they were mining the silverite. Bolby is currently has stopped mining silverite, and is now mining polyhalite exclusively. And I believe, as of this date, there have been no gas outbursts there. It's been a long time since I've worked there, but there was one a few years ago, which in the potash proper, where unfortunately resulted in the death of a very experienced miner. It was a major gas outburst. But so far in the polyhalite, it's pretty benign. That's not to say that there won't be some issues, and I'm sure, given their experience, that they will continue to watch out for it.
Lovely. Well, that's yes, that's something we'll keep an eye on, and maybe if there's any samples available, or if you want to try and get to the bottom of it, perhaps our institute might be able to help with that. We've just had a question in from YouTube regarding Cornwall. There are Lamprophyres in Cornwall. Are you aware of any record of outbursts where these have been intersected by Cornish mines? And is there anything to be concerned about regarding surface outcrops?
The latter point, no, because they're at surface, and I don't think they present any hazard at all. Other than you possibly falling over one that was below the tide mark, I suppose. But underground, yeah, I mean there are Lamprophyres in Cornwall. You're correct. They're a different type of Lamprophyre than the ones I've been speaking about. And there's a couple of good papers. If you are really interested in that, there's a couple of good papers. So do get in touch, and I can point you in the right direction of them. Looking at the lithologies, but they're very different in terms of their mica content and also the secondary minerals, those low temperature minerals that I talked about. So I wouldn't like to comment on what gases may be trapped within them as fluid inclusions, because almost certainly there will be fluid or melt inclusions within them. But I doubt that they're going to be there in any high quantity, and I doubt that they're going to present a problem, certainly at surface or underground. That they're also, relatively speaking, quite rare in Cornwall, whereas in the area that we're talking around in the platinum mines, there are hundreds going through a single mining area, and those are all individual dikes that we can map on, but we can't necessarily join them all up together in 3D space because they're quite difficult to try and connect the small scale features that run out. So I would say there's probably nothing to worry about. I think these are quite unique circumstances in terms of the intersection of the geology that we have here and the sheer quantity of dikes that we see in this location. Also, of course, the Lamprophyres are not, we don't think, the source of the gases. They're just a carrier for them. Because we've got lots of these dikes and faults, and there's quite a lot structurally going on in this area in the platinum mines, then it's probably more to do with how the gases are moving around, or in some cases getting stuck, rather than the Lamprophyre itself representing the danger.
Excellent. Are there any more questions?
On the YouTube, there's one from Dan Gallagher. Have you considered continuous gas monitoring, including pressure at a number of locations?
Yeah, so there's continuous gas monitoring with these basically fixed gas chromatographs that I spoke about. And the data are always being collected and always being recorded. But the problem is with these outbursts is that there doesn't seem to be a relationship between when there's an outburst and actually anything being triggered on the gas chromatograph, or us seeing a sort of spike in the methane concentration on the run up to or immediately after an outburst. We see it on the control blast, but there's no indicator for in order to use that as a forecasting tool, we don't think. That may just reflect that actually the volume of gases involved in these outbursts is relatively small, just they have quite a punch to them. And so again, maybe it's just below the level that the actual detector, the fixed detectors, and actually personal devices walking around underground can really detect. If there is a different type of sensor or monitor that could be fixed, then that would be interesting. But I would need to know more about what the detection limits for that were and what gases it was actually monitoring. But it's a possibility, but at present, the fixed sensors aren't much use to us for these outbursts.
Oh, excellent.
Oh, yeah, thank you, Hannah. Yes, are there any more questions? No, I don't think we have. I think, Hannah, that they're digesting all the information you've given, and I'm sure within 15 or 20 minutes there'll be thousands of questions going through people's minds. But thank you very much for a very, very interesting lecture. And can I call on Norman Jackson, please, to give a vote of thanks to Hannah?
Hannah, what a fascinating talk. Really, really interesting from me as a coal mining engineer principally, but we have so much in common. Before I listened to your talk, I was just looking at some of my records, and I first went into China in 2001. And between 2001 and 2017, there were 510 coal and gas outbursts, not explosions, coal and gas outbursts, resulting in 3,576 deaths. So outbursts are a problem not just in the hard rock mining, but also in the coal mining scene. I was fascinated in your thoughts about the future. How are you going to predict? And it's been a challenge that's presented mining engineers since probably since 1834, when the first outburst occurred in France. And we've been wrestling with this for an awful long time. And to hear the scientific way that you're trying to put some measure to it is very, very refreshing. There's one thing that I've found about gas that's predictable, that it's unpredictable. You can never lose your guard against gas. It'll stand up and it'll bite you. But I think that you're moving in the right directions from my experience. I think to be looking at things like atmospheric pressure and to be looking at the stress mapping of mines is vitally, vitally important. We found this in coal mining, that when we changed to roof supports, our roof supports to rock bolts, etc., then the stress calculations were absolutely imperative. But best of luck, not just to you in your research, but to Camboard in its difficulties at the moment, not training mining engineers. We need you all. We need you young people to be coming forward and taking the job forward in a very safe and effective manner. But thank you very much for giving your time and giving us such a wonderful talk.
Thank you, Norman. My pleasure. Thank you, everybody.
Oh, lovely. Superb. Yes, just if anyone is interested in doing it's a BSc in mine engineering at Campbell School of Mines, please do get in touch with them. I hear it's an excellent course. And then just to do the final notices again, please don't forget that our March lecture is on Thursday the 18th. It's going to be Living Construction on Biomaterials. We of course have a link will be sent out to our members shortly about the Young Persons Lecture Competition next Tuesday. A week today we have the Younger Members Lecture to which all are invited, and that's on living down on Sydney Island and doing survey work for the Antarctic Survey. And of course, more details will be shared online soon, but we of course have the 2-day Northern Energy Transition Conference with the Durham Energy Institute. So we'll hopefully see you all there. And that's it. I'll hand back to Steve.
Yes, yeah, well, thank you very much, Andrew. You kept us well informed there for what's happening in the future. And I hope everyone who's here tonight and listening tonight comes into those lectures and events also. So I'd like to thank you all very, very much for attending tonight, and especially to Hannah for such an absolutely wonderful lecture. And thank you very much once again, Hannah. Well, that's it. Good night, everyone. Thank you very, very much for attending. Take care. Safe trip. Bye now.